Hey guys, welcome back for another grade 11 chemistry lesson. Today's topic is going to be electronegativity. But before we hop into there, we're going to watch a little bit of a demo of what happens when you bring static electricity near water. Now, I know some of you guys might know this one already, but let's take a look anyways.
Frostbite Theater presents Cold Cuts, no baloney.
Just science.
Hi, I'm Joanna,
And I'm Steve.
and this is a piece of PVC pipe.
And this is a plastic cup that has a hole drilled into the bottom of it. So when I fill it with water, it leaks out of the bottom.
If I charge the pipe and then bring it close to the stream of water, the water is attracted to it. That's because water molecules are polar molecules.
Hey, pump the brakes there, lady. You're giving away my secrets. All right. So you can see the water bending towards the pipe. My question for you guys, why? Why is the water bending towards the pipe? So take a minute here. Think about that one. I mean, we talked about this in grade 9, right? Might have something to do with static electricity. Obviously, that thing is charged up. But what about water makes it attracted there? It's neutral, right? We know water's not charged. So why is water attracted? Now, she kind of mentioned part of it there. I didn't stop the video in time. It's polar, right? What does it really mean? So let's start here. Why does water bend towards a source of static electricity? Well, water is made of course, 2 hydrogens and 1 oxygen. So those are the atoms we have in water. The atoms are arranged, if you were to look at the actual shape of water, they're arranged so that one side of the water molecule has more electrons than the other. So here's your oxygen, here's your 2 hydrogens, and this here, this line, represents a bond. And a bond is, in this case, 2 electrons being shared. So they share a couple electrons there. But here's the deal. Oxygen likes electrons a little bit more. So those electrons that are in the bond end up being pulled closer to the oxygen. So you end up with one side of the water molecule having slightly more electrons than the other. So you end up with a slightly, this symbol here is the Greek symbol delta. They use it for like slightly. So it's a partial negative charge. And this side ends up with partial positive charges. And so electronegativity is the ability of a single atom in a chemical bond to attract electrons. So if you look back here, our oxygen must have a lot of electronegativity because it is pulling the electrons towards itself. It's very electronegative. In our water example, oxygen is more electronegative than hydrogen is. So the electrons are more attracted to oxygen than hydrogen. Kind of what we just talked about there. That's this section. So shared electrons in the bond are pulled towards the oxygen. And as a result, the hydrogen side is slightly more positive. The oxygen side is slightly more negative. Now, it doesn't have a full-on positive charge. The oxygen side doesn't have it's not like it's missing an electron or has gained an extra electron. It's just a very slight charge. You could measure it as like a fraction of a charge if you really wanted to get specific. So when a molecule has different charges on different sides, that's where that word polar comes in. It has poles. It's got a positive side and a negative side. Kind of like a magnet has a north and a south. You know, we have a north pole and a south pole. That molecule has a positive pole and a negative pole. Slightly different charges on slightly different sides. Now, if your molecule is the same on all sides, then we say it is non-polar. I'll show you some examples of that in a bit. But first, here's our beautiful table of electronegativity. So things that really like electrons would be over here. Fluorine's the most at like a 3.9 something. It's a little fuzzy. I think it's like a 3.98. It's way up there. And you can see oxygen also very high, chlorine very high. So the closer you get to this corner, the more electronegative you are. Hydrogen is also fairly electronegative, but if you check this out, hydrogen's at a 2.2, oxygen's at a 3.44. Oxygen is more electronegative. That's why oxygen pulled those electrons. And if you were to match an oxygen with something like, I don't know, a potassium at 0.82, you can bet that that oxygen would be absolutely tearing at those electrons, right? It would pull them super far over. So far, it might actually steal them. Oh, wait a second. metal plus non-metal, ionic bond, that's actually what it does. It steals those electrons straight up. So when you're bonding non-metals together, you can check your electronegativities, and it would tell you, is it actually like, which side would be more electronegative than the other? If it's the metals and the non-metals, you don't have to worry about it so much because they've actually straight up stolen the electrons. So it's pretty easy to tell which side would be the negative and which would be the positive. Metals are almost always going to be your positive side, and your non-metals would almost always be your negative side because this is where all of our electronegativity is. Moving on. 2 atoms. We bond those together. Whichever one has the highest electronegativity attracts electrons the strongest. We kind of just talked about that. The side of the molecule that has that electronegative atom will be negatively charged, right? It's pulling electrons. It's pulling negative charges towards it. Electrons. If electronegativities are almost the same or actually the same, then the substance would also be non-polar. Just like a polar here. Hydrogen and chlorine. Quick check. Chlorine is here at 3.16. Hydrogen's at 2.2. They're different numbers. That's going to be polar. Oxygen. So you can see, we just looked at that and we know that the hydrogens are going to pull this way. So we're going to have negatives on that side. Same with ammonia, nitrogen trihydride, ammonia. The nitrogen, if we check it out, is a 3.0. Hydrogen, again, is a 2.2. So nitrogen wants some more. It's going to suck all the electrons up and end up with the negative side. Let's check these out. Nitrogen bonded with nitrogen. Well, nitrogen is going to have the same electronegativity on both sides, so neither side is going to be able to pull electrons. They're going to stay equal in the bond. There's going to be no polarity, no positive or negative side. Let's check this one. Carbon and oxygen. Carbon's at is that a 2 or a 3? It doesn't actually matter. I think it's a 2. 2.55. Oxygen's at 2.2. So carbon wants to pull on the electrons. But if electrons go slightly this way and slightly this way, so let's say this side ends up, oh yeah, carbon would pull on them. That's right. Carbon and oxygen? I'm looking here. Oxygen wants it. I looked at hydrogen. My bad. Oxygen wants it more. So oxygen's going to, I thought that seemed off. Oxygen wants electrons. Electrons go this way. This ends up negative. This ends up negative. Wait a second. Does it have a positive side and a negative side? Oh, it doesn't. The positive bit would be in the middle. It's kind of equally balanced. There's an equal pull of electrons in either direction. And because it's equal in either direction, we say it's nonpolar. So this is equal electronegativities. This is equal pull in opposite directions. So if the molecule is symmetrical, you won't get polarity. And that's the same thing we have down here. Chlorines are going to pull a lot harder than carbon will because they're right close to the fluorine, but it's pulling in equal directions. So it's going to be slightly negative all around the outside. It's not going to have a positive side. If it doesn't have a positive side along the outside of the molecule, well, then we say it's nonpolar. You got to have a positive side somewhere to be polar. So what does this have to do with states of matter, right? That's what we're talking about. Well, polar molecules have stronger IMF, stronger intermolecular forces, because their positive ends and their negative ends, oh, that's an M, are attracted to each other, right? If I look at water, and this end is slightly negative, this end's slightly positive. If I were to line another water up like this, look at that. My positives and negatives are attracted right here, delta negative, and these ones are attracted right there. They're going to stick together. They've got a lot of intermolecular forces there. We got a lot of positives and negatives in between the molecules, intermolecular, holding them together. They're more likely to be solids or liquids. They have high intermolecular forces. They're going to be a solid or a liquid. Non-polar molecules have weaker intermolecular forces. They don't have nearly this strength of positives and negatives holding them together. So there's a lot less there to hold them. And so because they do not have that electrostatic attraction between poles, they're more likely to be gases or a really volatile liquid. In chemistry, volatile doesn't mean like angry or explosive. Volatile liquids have a low boiling point. It means they boil really easily, which you can flip side of that. It means they evaporate quickly or have a high vapor pressure. We're going to talk a lot about vapor pressure today. Just give me a couple of slides here. So an example of this would be like a hand sanitizer. Like you put that on your hand, you rub it in and whew, it's gone, right? And that would be a high vapor pressure. So it's a liquid, but it evaporates really fast. So that would be we'd say that's a volatile liquid. All right, on to vapor pressure. Now, let me start by showing you guys a little something cool. How to boil water with ice. There we go.
Today we're learning how to boil water with ice. We first need to warm up the water inside a sealed conical flask, almost to the boiling point. The water needs to be really hot. Once the water in the flask is hot enough, take the flask and you flip it.
So you can see water there, not boiling, right? They just heated it up like crazy.
Make it steady, and we put an ice cube on top of it, and suddenly
As soon as the ice cube touches, the water starts to boil.
See all the bubbles. So what's happening? The pressure in the top
Hey, don't give away my secrets. Pause.
our flask
No, pause.
is suddenly dropping.
Oh, it's just a little leggy. Okay. Whew, we're going to talk about what happens there. So they heat up the water like crazy. They flip the flask upside down. Just, I guess that's easy to put the ice on it. They put the ice on the bottom, and it goes from really hot water to boiling water right away. And we're going to talk about why that happens, and it has to do with vapor pressure. So all liquids have a certain amount of particles which are escaping all the time. If we have a liquid sitting there, some of that liquid is escaping into the air. So we talked about like average kinetic energy, right? So if you look at a liquid, all those molecules have a little bit of average kinetic energy. Everything's moving a bit, but average, right? Some things will be slower, others will be faster. Sometimes a particle is fast enough, it gets just enough energy to escape the intermolecular forces of the surrounding liquid, which means it can fly away now. It's not being held. We call that evaporation. It happens to everywhere. You leave a glass of water out at room temperature, eventually that water will disappear. It doesn't have to be boiling. It takes a lot longer if it's not boiling, but everything evaporates at some rate. Now, those particles, as they fly off, they create pressure, which pushes on the surrounding air, right? It doesn't fly off into the void. There's air sitting above a beaker or above a glass. And so that air is bouncing off the water. The surface of, let's say water, it could be any liquid, but the air is bouncing off the surface of that water. And so when your particle tries to escape, it creates a pressure which pushes off the water, right? Or off the air. It's bouncing off those air molecules. We call that vapor pressure. So it's how much pressure the evaporated particles have pushing against the air. And the air will push back, of course. It's got its own pressure. We call that atmospheric pressure. So the more atmosphere you have above you, the higher your atmospheric pressure is, and the more it's pressing down on that water. So particles, in order to escape, have to push against both the intermolecular forces of whatever fluid it is and the atmospheric pressure in order to escape. So I don't not only have to beat the intermolecular forces, I also have to be flying fast enough that if air comes and bounces against me, it doesn't push me right back into the liquid where I would become part of the liquid again. So I got two kind of sides to things here. The IMF and the atmospheric pressure that I got to beat. So let's look at boiling. What happens if we increase the temperature of a liquid? We start heating it up. Well, if we increase temperature, we're putting in energy, right? So the average energy of the particles increases. If the average increases, well, therefore, more particles have enough energy to escape. So more particles should be able to escape. You go from water just sitting there to maybe water steaming. You're seeing even more start to escape. There is a increase in vapor pressure. You have more particles flying off at higher speeds That means you've got more vapor pressure pushing against the atmospheric pressure. So, okay, what does this have to do with ice, though, right? How does this explain why water boils when you put ice on top? Well, when you cool the air, let me draw this. Let me draw that flask again. There we go, fancy. Here's our water. Here's our plug. So this here, hot water. And what would this be? Well, that was just boiling. That would be hot air, right? Hot air is going to have a lot of pressure. It's going to be bouncing around quite a bit. If I put an ice cube up here, well, that's not going to be hot air anymore. It's going to start to cool down. When you cool the air above the water, well, now that atmosphere, quote unquote, the number of air molecules bouncing, as that cools down, some of those start to not, like, it doesn't push as much. They slow down. Their average kinetic energy decreases as you cool it down, so you have less bouncing off the liquid. So you haven't changed the vapor pressure of the liquid, but you have changed the atmospheric pressure in the bottle. When you reduce atmospheric pressure, well, then there's less pressure holding the particles back. They can start to escape more easily. So what you've basically done is lowered the boiling point of water by changing the pressure inside the bottle. If you increase the pressure, it takes longer for water to boil. That's how an Instapot works, or a pressure cooker. You pressurize water so that it doesn't boil at 100 anymore. Maybe it boils at 110. All of a sudden, I'm cooking at a higher temperature, so things cook faster. Right? If I have rice in water, if I boil it at 100, maybe it takes 20 minutes. But if I can somehow find a way to boil it at 130, now that's going to cook in like 5, maybe 8 minutes, right? It cooks faster. But we just said, when you're boiling water, it boils at a certain temperature and it doesn't change, right? That has to do with the exothermic and endothermic nature of boiling. But if you change the pressure, you change the boiling point. Still doesn't mean water can go above the boiling point, but it would go up to and sit at whatever that new boiling point is. So the ice does the opposite of that. It lowers the atmospheric pressure and then lowers the boiling point. So this water, let's say it was at 95 degrees, that won't boil with regular pressure. But if you reduce the pressure, all of a sudden that water starts boiling. Now this leads us to normal boiling point. If water can boil at any temperature depending on the pressure, well, we've got a problem. What's the boiling point of water now? So we call that the normal boiling point. It's the temperature needed for the vapor pressure of the liquid to equal the pressure of the atmosphere, regular atmospheric pressure. And that for us, we know, is about 100 degrees Celsius, right? When the liquid that you are trying to boil pushes harder on the atmosphere, then the atmosphere pushes back. So here's my liquid. When it pushes harder, then the atmosphere pushes back, then the particles start to escape as a gas. And it doesn't have to be particles at the top. Particles inside start to turn into gas. And that's why you see bubbles. So take a minute here. Why is it easier to boil water in the mountains around Banff than it would be to boil water here in Winnipeg? Pause the video here. Take a minute. See if you can figure this out. Why is it easier to boil water in the mountains around Banff than it would be here? So in Banff, you're at a higher elevation, which means less atmosphere above you. You're up in the mountains, there's less air above your head before you hit space, right? Which means less atmosphere pushing down, a lower atmospheric pressure, which means the temperature required to get your water's vapor pressure to equal the atmospheric pressure is lower. I don't need to go all the way to 100 anymore. Maybe 95 degrees is enough to get things to boil now that I have less atmosphere. This also means rice would cook slower in Banff, unless you were using a pressure cooker or something, because the water wouldn't be at 100, it'd only be at 95. And so we got a little bit of a difference here between evaporation and boiling. In evaporation, bubbles can't form because the vapor pressure is less than the atmosphere. I have the atmosphere trying to hold all this stuff into place, and so only 1 or 2 particles can escape if they happen to be on the really high end of average speed. bubbles aren't going to be able to form because atmospheric pressure would push them right back down and into the liquid. But if my vapor pressure is really high and it can overcome atmospheric pressure, well, then I can start to form bubbles. Because vapor pressure is so much stronger, these can rise right out and into the atmosphere because the atmosphere isn't going to hold them in place. So that's the difference between evaporation and boiling. And that also wraps up today's lesson about electronegativity, boiling points, and energies. So thanks for watching, and I will see you guys shortly.